Welcome to this video presentation on heat exchangers. Today we'll be working through example 2, which focuses on calculating the required tube length for a counterflow heat exchanger. Let's look at the problem statement. We have a counterflow heat exchanger that cools 12.5 kilograms per second of air from 540 degrees Celsius to 146 degrees Celsius. This heat exchanger contains 4,200 tubes, each with a diameter of 30 millimeters. The cooling water enters at 25 degrees Celsius and exits at 75 degrees Celsius. If the water side resistance to flow is negligible, our objective is to calculate the tube length required for this duty. We are given a correlation for turbulent flow inside tubes. Nusselt number equals 0.023 times Reynolds number to the power of 0.8 times Prandtl number to the power of 0.4. Additionally, the properties of air and the average temperature are provided. Density is 1.009 kilogram per cubic meter. Specific heat capacity is 1.0082 kilojoules per kilogram degree Celsius. Dynamic viscosity, mu, is 2.075 times 10 to the power of minus 5 kilogram per meter second. And thermoconductivity, K, is 3.003 times 10 to the power of minus 2 watts per meter degrees Celsius. Now let's begin with the solution by outlining the given parameters. The mass flow rate of the hot fluid, mh dot, is 12.5 kilograms per second. The inlet temperature of the hot fluid, TH1, is 540 degrees Celsius, and the outlet temperature, TH2, is 146 degrees Celsius. For the cold fluid, the inlet temperature, TC1, is 25 degrees Celsius, and its outlet temperature, TC2, is 75 degrees Celsius. The number of tubes, N, is 4,200, and the diameter of each tube, D, is 30 millimeters. Our goal is to find the tube length, L. The first step is to calculate the Reynolds number, RE. The general formula for RE is equal to rho VB over mu, and we can express rho times V as a mass flow rate per unit area. So rho times V equals M divided by N times A, where A is the cross-sectional area of the single tube, and substituting into the Reynolds number, RE equals M times D divided by N times A times mu, so that the cross-sectional area A is pi over 4 times D squared. Now when we plug in the numerical values, we get the Reynolds number is equals to 6087.4. Next, we calculate the Prandtl number, which is mu Cp over K. Substituting the values, this gives us a Prandtl number of approximately 0.6966. Now we can find the Nusselt number using the given correlation for turbulent flow, and this Nusselt equals 0.023 times RE to the power of 0.8, Prandtl number to the power of 0.4. So substituting our RE and Prandtl values, and then calculating, we get a Nusselt a number of approximately 21.2. And from the Nusselt number, we can now solve for the convective heat transfer H. So therefore, rearranging and then plugging in the values, we get H to be approximately equal to 21.222 watts per square meter degrees Celsius. Now, since the water side resistance to flow is negligible. The overall heat transfer coefficient U is approximately equal to the convective heat transfer coefficient H we just calculated. So U equals 21.22 watts per square meter degree Celsius. Next, we calculate the logarithmic mean temperature difference, which is given by the formula there. And when we plug in the values and perform the calculation, we get ln dt to be approximately equal to 255.5 degrees Celsius. Finally, we can now be able to calculate the tube length L. First, we determine the rate of heat transfer Q, which can be expressed in two ways, using the heat capacity rate of the hot fluid or using the overall heat transfer coefficient and LMDT. So Q equals M H dot times CPH times the temperature difference. And then rearranging to solve for L, we get L equals the formula that is shown there. And once we plug in the values and perform the calculations, we get L to be approximately equal to 2.31 meters. And this is our final answer. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so you don't miss out on our latest uploads.